This lecture is all about common source amplifier. I'll explain working and frequency response of common source amplifier working at high frequency band. I will also derive expression for the 3 dB upper cutoff frequencies. In my last lecture number 10, I already explained behavior of common source amplifier working at low, mid and high frequencies. At mid frequencies, we don't bother about the effect and presence of coupling, bypass and internal capacitors, because at mid frequencies, these coupling and bypass capacitors, they behave as short circuits, and these internal capacitors, they behave as an open circuit. We also ignore the transient effect of charging and discharging of these capacitors in the derivation of current voltage characteristics and relationship for Mosfet. But at high frequencies, the situation is quite different. At high frequency band, this common source amplifier exhibits low pass characteristics, where after some frequency, the gain starts falling with this rate, minus 20 dB per decade. The attenuation of gain beyond this frequency is because that the internal capacitors, they don't behave as an open circuit. This is called upper 3 dB cutoff frequency, where the gain starts falling by 3 dB. Let me explain the reason for the presence of these internal capacitors in Mosfet. This is the basic structural diagram for Mosfet. This is source, drain, and this is substrate region. And the source, gate, drain, this is body or substrate. And the very basic parallel plate capacitor can be visualized between gate and N-type inversion channel separated by silicon dioxide layer. This is a capacitor we have used for the derivation of the current voltage relationship for Mosfet in my earlier lecture also. Anyway, there are two types of internal capacitor connected with the Mosfet. The very first one is related to gate and the second one is related to substrate. This is a very symbolic diagram between gate, source, drain and body. The capacitance due to gate are between gate to source, gate to body, gate to drain, denoted by CGS, CGB, CGD. And C0 is because the overlapping part of source and drain region by gate. This overlapping is due to self-aligned gate technology, and this overlapping will give rise to this capacitance. Now let us compare and study the relative magnitude of these capacitances. And Mosfet output characteristics, the very first example is from cutoff region, where this VGS is less than threshold voltage. In that case, there is no channel. So there is no reason for capacitance between G and S and G and D. That's why CGS and CGD would be 0. And the whole capacitance will be between gate and body, which is equal to COX WL. COX is the capacitance per unit area, and W and L are width and length of the channel. The second part, triode region, where this VDS is less than VGS minus VT. In this situation, there is channel but of uniform width. In this case, this CGS and CGD will be equal and they will share the whole capacitance equally. CGS will be equal to CGD is equal to half the total capacitance between G and B. Third case, saturation, where this VDS is equal or greater than VGS minus VT, where pinch off condition is there. In that case, the shape of channel would be triangular. In that case, this CGD would be 0 and CGS will be 2/3 of the whole capacitance. Anyway, these are the values and facts just for reference, and I am simply putting them for explanation purpose. And for overlapping, this part shows the dimension of the overlapping only. This is L0. This is very small. Now, second part, this is related to substrate. This is p-type, this is n-type, this is n-type. So there is one p-n junction here and there is one p-n junction here. In silicon on insulator technology, when on a single wafer so many MOS devices are fabricated, in that case B or substrate is connected to most negative power supply in case of NMOS, or it's connected to most positive power supply in case of PMOS. In those two cases, this VSB and VDB would be reverse biases for this junction and this junction. These two junctions under reverse biasing will have junction capacitances and generally known as between S and B and D and B, and these are here. This is related to substrate. This is CSB and CDB between source and body and drain and body. This is called body effect. These are also called junction capacitances, and these are the expression for CSB and CDB. In case when body and source terminals are interconnected, these two would be 0. There would be no reverse biasing. In those cases, this value will be equal to CSB0 and CDB will be CDBO. In most of the cases, body and source terminals are interconnected for convenience. In this lecture also, I also assume that body and source terminals are interconnected. So this was all about the effect and reason for internal capacitor and the attenuation of gain in high frequency band. And now I'll explain the structure of a small signal equivalent circuit for common source amplifier working at high frequency band, incorporating the effect of these internal capacitors there. This is the modified small signal equivalent circuit of common source amplifier working at high frequency band. All internal capacitors have been incorporated into this equivalent circuit. This is gate, source, body and drain terminals. R0 is the output resistance of the device, and GM/VGS is the voltage control. Current source entirely depends upon input voltage VGS. This is the input voltage between gate and source. This input voltage is a function of Laplace variable in S domain, and CGS is the internal capacitor between gate and source. CGD is the internal capacitor between gate and drain, and VBS is the potential difference between body and source. CSB and CDB are the transition capacitances because of body effect. And this is again voltage controlled current source, and this current source is because of body effect. So this circuit looks very complex and it is very easy on SPICE simulation, but it's very tedious when calculations are done by hands only. When body and source terminals are joined together, interconnected, in that case this circuit will be further simplified into very simplified structure where this capacitance and this current source have been omitted, and we can ignore the presence of CDB because of its of very low value, and this will behave as open circuit. So this is the final form and structure of a small signal equivalent circuit of common source amplifier working at high frequency band. And generally this CGD is called bridge capacitor between gate and drain, and CGS is generally known as the shunt capacitor between gate and source. So this is the final form, and we will be using this equivalent circuit for our further analysis. This is all about quick revision about important facts and expressions in S domain, which I'll be using for the derivation of the expression for 3 dB upper cutoff frequencies. And this expression is about transfer function for voltage gain, and this expression contains so many Z's and so many P's. All Z's are zeros and all P's are poles. For a network, low pass network containing 2 poles, the denominator of transfer function of voltage gain can be simplified in this manner. And P1 and P2 are poles. Suppose P1 is dominating pole, that means P1 is far less than 10 times P2. In this case, this term can be omitted, and this is a simplified expression for the denominator containing Laplace variable and two pole frequencies omega h1 and omega h2. This expression is very important for the derivation of 3 dB upper cutoff frequencies. For a low pass network, if the denominator is quadratic expression in terms of Laplace variable s, then by comparing the coefficient of s and s square, the expression for 3 dB upper cutoff frequencies can be obtained easily. Next point about a low pass network of the first order, very simply, it's called also single time constant circuit, and the transfer function for this type of network can be written this way, where m is the gain at the mid frequencies and this omega h is the 3 dB upper cutoff frequencies. It is shown here. This is the frequency response for low pass network of the first order, and beyond this frequency gain starts falling with this rate minus 20 dB per decade. At this frequency gain falls by 3 dB. For example, of low pass network containing single loop containing only two elements R and C, the expression for omega h is very simple, 1 by RC. This concept is very important, and this is very simplified network, and this can be used in those circuits where so many loops are formed at the input and output stages. By using Thevenin theorem, we convert all loops into a single loop containing one Thevenin equivalent voltage source and one Thevenin equivalent resistance across the terminals of capacitor. In that case, this can be written further as R, TH and C equivalent, where RTH is the Thevenin equivalent resistance across the terminal of C equivalent, and C equivalent is the net capacitance when we are using Miller theorem to convert bridge capacitance into shunt capacitance. That theorem is different theorem, Miller theorem. On the next page, I will be explaining Miller theorem. This is about Miller theorem, which is used to convert any bridge impedance into equivalent input impedance at the input end and equivalent output impedance at the output end. The expressions for Zi and Zo are given as here. This is Zi and Zo in terms of Z and the voltage gain. In our high frequency small signal equivalent circuit, we have one bridge capacitor known as CGD between gate and drain. We can also convert this bridge capacitor into equivalent shunt capacitor at the input end and one at the output end. For CGD, the value of Z, this is the value of Z and this is the voltage gain, and by using these equations, we get the expression for Zi. This is the equivalent shunt impedance at the input end because of bridge capacitance CGD, and by studying the denominator we understand the value of Ci. This is the equivalent shunt capacitance at the input end because of bridge capacitance CGD, and this factor is called Miller factor. Similarly, we get the expression for Zo. This is the equivalent shunt impedance at the output end because of bridge capacitance CGD, and by studying this denominator we understand the value of equivalent shunt capacitance at the output end because of bridge capacitance CGD. In this way, this bridge capacitance CGD can be converted into equivalent input capacitance Ci and output capacitance Co in terms of CGD both ways, CGD and CGD here. And this is called Miller factor. This is also called Miller factor. This Bode plot shows relative position of two poles. This is Bode plot, and this is dominant pole, this is the second pole. At the dominant pole, gain falls by 3 dB, and after first pole or dominant pole, the rate of attenuation is minus 20 dB per decade. After second pole, the rate of attenuation is minus 40 dB per decade. For being dominating, the pole should be at least 1 decade apart from the second pole. In the present case, these two upper 3D frequencies are very well and widely separated, and they are distinct also. Now we can say this is a dominant pole. This is all about unity gain frequency, generally known as Ft. This is very important parameter for Mosfet. At this frequency, the short circuit current gain of common source amplifier at high frequency band becomes unity. For the derivation of the short circuit current gain for common source amplifier, we have to modify the existing small signal equivalent circuit for common source amplifier. For that, we have to apply one current source at the input, and we have to remove the load, and we have to short circuit the output terminal. Since output terminals are short circuited, that means these two capacitors are in parallel, because this point and this, all these points are at the same potential, they are in parallel. And this potential difference will appear across the parallel combination of CGS and CGD. Now, and this is GMVGS, this is the voltage control current source, this is the output resistance of the device. Now, output current, this is the output current, this is passing through the short circuit path. So this is the expression for output current, and input voltage VGS is calculated by using the simple ohmic law. This is a current, and this is 1 by S, this is the impedance of the combination of these two capacitors. So this is the input voltage VGS. Now we can define short circuit current gain, that is AIS. This is the ratio of output current to the input current. So this is the output current, this is the input current, and this is the expression for short circuit current gain. Can be written in a very simplified format in S domain. Now, from this expression, we can write the expression for unity gain frequency. This is omega t, this is the expression. And at omega t, at unity gain frequency, this short circuit current gain becomes equal to unity. And this is the frequency response at omega t, current gain in dB becomes 0. And this is the response showing the effect of frequency on the short circuit current gain. So this was all about unity gain frequency FT for Mosfet. Now I will derive the expression for upper 3 dB frequencies for common source amplifier working at high frequency band. This is the most fundamental circuit diagram of common source amplifier, where CC1, CC2 are coupling capacitors and CS is the bypass capacitor. At high frequency band, these three capacitors will behave as a short circuit. And this is a small signal equivalent circuit of common source amplifier at high frequency band, where CGS and CGD are two internal capacitors. This is shunt and this is bridge capacitor. This is the input voltage source, and this is the internal resistance of input voltage source. VGS is the potential difference between gate and source. RG is the bias resistor, and GMVGS is the voltage control current source. R0 is the output resistance of the device. RD is the resistor connected to drain, and this is RL is the load resistor. Output is taken at the drain end, and this is a source. For the determination of upper 3D frequency, I will be using S domain analysis. Now considering gate node, and this is the expression as per Kirchhoff current law, where this current is equal to this plus this plus this. From this expression, we get the expression for VGS, the potential difference across gate and source. Here, this R is the parallel combination of RS and RG. Similarly, considering drain node, and this is the expression as per Kirchhoff current law, sum of the current meeting at drain node is 0. From this expression, we get the expression for VGS again, where this RL dash is the parallel combination of R0, RD and RL. Now, I will equalize these two equations to eliminate this term VGS. Then we will be in a position to have transfer function of voltage gain. Just on the next page. This is expression for transfer function of voltage gain in S domain. So this is very lengthy or complex looking expression. Second step, then third step after simplification. I have omitted few steps for simplification. Anyway, the denominator of transfer function of voltage gain is a function of Laplace variable, and it has quadratic term in S also. I also explained earlier that by comparing the coefficient of S and S square, we can write down directly the expression for upper 3 dB frequencies. For example, comparing the coefficient of S. So this factor will come here, and this expression is for omega H1. This is the first upper 3 dB frequency. Similarly, by comparing the coefficient of S square, we get the expression for the product, By substituting the value of omega h1, we get the expression for omega h2. This is second upper 3 dB frequency. One important point is here, the value of CGD over here. If this increases, that means omega h1 decreases and omega h2 increases. Increment in the value of CGD causes poles to split apart, making this omega h1 as a dominating pole. And the whole process of S-domain analysis is very tedious for manual calculation, but this gives very accurate result. On the next page, I'll describe different method that's called open circuit time constant or zero value method. So this is all about open circuit time constant or zero value method. And this is a transfer function of voltage gain containing two poles. And this in terms of physical frequencies, and this is the opening of bracket, and this factor can be omitted because the numerator is far less than the denominator. So this is the final expression for the transfer function of voltage gain. AM is the gain at the mid frequencies. And this is basically first order low pass filter and low pass network. And we can write directly upper 3 dB frequency, and this is the expression for upper 3 dB frequency. And 1 by omega is time constant. There are two capacitors. So this is the time constant of the first capacitor, and this is the time constant for the second capacitor. This is the summation of time constant. And this is the value in Hertz. Now, to use this open circuit time constant or zero value method, we have to understand one important point. If we set the value of capacitance of any capacitor equal to 0, then it behaves like an open circuit. Now in our present case, there are two capacitors, so there are two steps involved. The very first step is consider only one capacitor. Suppose I am considering this capacitor. Then we have to put the value of this capacitance equal to 0 so that this will behave as an open circuit. Then this is the resistance seen by this capacitor, or technically this is the Thevenin equivalent resistance across the terminals of this capacitor. Now select this capacitor and set the value of this capacitance equal to 0 so that this will behave as an open circuit. Now this is the resistance seen by this capacitor, or technically this is the Thevenin equivalent resistance across the terminals of this capacitor. So this is the summation of time constant. In this way, this method will give one approximate value of upper 3 dB frequency. This is very simplified method and very useful when we are not sure about the status or position of any dominant pole. Then this will give you only one approximate upper 3 dB frequency, which is for a quick analysis, it's far good. Now I will explain how to use open circuit time constant or zero value method for the determination of upper 3 dB frequencies for common source amplifier working at high frequency band. This is small signal equivalent circuit for common source amplifier. There are two capacitors, and in the process we have to select one capacitor and think or consider another capacitor as an open circuit. Suppose I am selecting this, I'll consider this as an open circuit. Then I will determine the Thevenin equivalent resistance across the terminal of CGS, or Thevenin equivalent resistance presented to CGS when CGD is open circuited. Now I will select this one and consider CGS as open circuit. Then I will again determine Thevenin equivalent resistance presented to CGD across the terminal of CGD. In this way, we will have time constant for this as well as time constant for this. And for the determination of upper 3 dB frequencies, we need summation of time constant for the capacitors involved in the circuit. I'll explain on the next page. I'll be selecting this first, then I will select this. Then I'll be explaining how to determine Thevenin equivalent resistances presented to this as well as this separately. Now I will determine the time constant for CGS and considering the bridge capacitance between G and D as open circuit. And as per Thevenin theorem, the input voltage source is short circuited and current source is open circuited. Now we have to find Thevenin equivalent resistance across the terminal of CGS. and that is a parallel combination of RS and RG. So this is the Thevenin's equivalent resistance RGS across the terminal of CGS. This is parallel combination of RS and RG. Now the time constant for CGS is Thevenin equivalent resistance into the capacitance of the capacitor CGS. So this is the expression for time constant for this capacitor. Now I will derive the expression for time constant for another capacitor, that is known as bridge capacitor CGD. In that case, this will be termed as open circuited. Now let us have time constant for capacitor, bridge capacitor CGD, and this capacitor between gate and source is considered as an open circuit. And since we are dealing with the dependent sources, and as per Thevenin theorem, the CGD is replaced by test voltage over here, and this voltage source is short circuited, and this is the voltage controlled current source GMV, and the combination of these three resistors is replaced by RL dash. Now considering this loop, and as per Kirchhoff Voltage Law, we write this potential difference is equal to the sum of the potential differences in this loop. So this is the expression for Vx, and after simplification, and now from this expression we get Thevenin equivalent resistance RGD. This is the Thevenin equivalent resistance across the terminals of this capacitor, bridge capacitor CGD. So this is Vx by Ix. So this is the expression. Now time constant for CGD is, this is the Thevenin equivalent resistance across the terminals of the CGD, and this is the capacitance of bridge capacitor connected between gate and drain terminals. So we are now in a position to have time constant for both the capacitors. Now we can define and determine upper 3 dB frequency on the next page. Now we have time constant for both the capacitors, and we can define upper 3 dB frequency for common source amplifier working at high frequency band. So this is the expression for upper 3 dB frequency, and this is the time constant for this capacitor, and this is the time constant for this capacitor. So this method, open circuit time constant or zero value method, gives only one approximate value of upper 3 dB frequency, and this is very good for quick analysis, and this method is very useful in the cases where we are not sure about the position of dominant pole. On the next page I'll explain one more method for quick analysis based on Miller's theorem. Now I will be using Miller theorem to derive expression for upper 3 dB frequencies for common source amplifier at high frequency range. This is one of the easiest method to study behavior of common source amplifier at high frequency range. This is a small signal equivalent circuit for common source amplifier containing two internal capacitors at high frequency range, and we use Miller theorem to convert any bridge capacitor connected between gate and drain into two shunt capacitors. This is bridge, and these two are shunt capacitor, Ci at the input end, Co at the output end. This RL prime is the parallel combination of these three resistors, and these two are in parallel, that's why there is a summation sign combined together. And across these 2 points on the left hand side, looking this way, we have converted the whole circuit using Thevenin theorem. So this is a single loop, and this is a single loop. On the input side and output side, these two loops or these two circuits show first order low pass networks, and Ci and Co are the expression which I already derived in this lecture. One more point, this is the total internal resistance, or this is the Thevenin equivalent resistance seen by this combined capacitance or across the terminals of these 2 points, across the terminals of equivalent capacitance between G and S. On the next page we will write the expression for upper 3 dB frequencies. Using the concept of first order low pass network, we can write directly the expression for upper 3 dB frequencies for this circuit. And this is input loop, that is output loop. For input loop, this is the first upper 3 dB frequency, where this is a net Thevenin equivalent resistance across the terminals of this capacitance. And At the output loop, this is the expression of second upper 3 degree frequency, where this is the net Thevenin equivalent resistance across the terminals of this capacitance. These are the expressions for upper 3 degree frequencies using Miller theorem. When compared with the S domain analysis, these are rather approximate values and there may be some errors. The reason is very simple, because Miller theorem does not consider splitting of poles and separation of poles. Anyhow, this was all about the analysis of performance of common source amplifier at high frequency band.